Well, let's learn how to calculate the standard entropy change for the reaction. So let's remember we did something similar to this in 1A. The standard enthalpy change for a reaction, that was delta H0 reaction, is the change in enthalpy for a process in which all the reactants and products are in their standard states. That's what the little degree sign there means. So what were those standard states? Here's the definitions. For a gas, the standard state is the pure gas at exactly 1 atmosphere. For a liquid or a solid, the standard state is the pure substance in its most stable form at 1 atmosphere and the temperature of interest. Often that's 25 degrees Celsius. If it doesn't say, you could assume 25. Otherwise, it should specify. What about if you have something that's in solution? A substance in solution, the standard state definition is that in solution with a concentration of 1 mole per liter. So those you should remember from 1A. So the standard entropy change for a reaction is the change in entropy for a process in which all the reactants and products are in their standard states. That's really similar to the standard enthalpy change definition, right? There we're looking at enthalpy with everything in their standard states. Here we're looking at entropy, the change in entropy, but again, all the reactants and products in their standard states. Entropy is a state function. We've mentioned that. State function means that how you get there doesn't matter. It's just where you started and where you end up. So delta S is a state function. So if we have the entropy of the products in their standard states and subtract the entropy of the reactants in their standard states, that will give us the change in entropy. Well, we need to define standard molar entropies because the amount of entropy does depend on the amount of substance. With enthalpy, I don't know if you remember this, we kind of had to make up what 0 was because you can't, there's no absolute 0 for enthalpy. And so what we said was the elements in their standard states, that's 0 enthalpy. And we can measure the change from there, but there was no absolute 0 that we could measure from. It's, kind of comes down to a lot of things are really relative. You talk about how fast is something moving. Well, relative to what, right? Relative to this part of the Earth, which is also moving, or relative to some imaginary stationary point in space, it changes. And so with enthalpy, we have no actual 0 to measure from. But for entropy, there is an absolute 0. So this brings up the third law of thermodynamics, which states that the entropy of a perfect crystal at absolute 0, 0 Kelvin, is 0. Absolute 0 is the temperature at which molecular motion stops. So this perfect crystal, at 0 Kelvin, these atoms or molecules are not vibrating even. They're fixed in position. They are all ordered. There is only one possible arrangement for them, and they're not vibrating. There's only one place to put energy. So W is 1. There's one arrangement. Boltzmann's definition of entropy, entropy equals a constant times the natural log of W. Well, if W is 1, the natural log of 1 is 0. The natural log of 1? Had a little minor brain fart there. Yes, that's true. So, yeah, it happens a lot. Should quit. I don't know. Anyway, so entropy is 0 here. There's only one possible way to arrange the atoms, and there's no movement at all. So we have this absolute 0 for entropy. Entropy is an extensive substance, meaning it depends on how much substance there is. Can you think of another extensive property? A property that depends on how much there is. Mass? Can you think of an intensive property? Does not depend on how much substance. Density. The density is the same whether you have a little bit or a lot.
Unless you have a lot.
Well, yeah, we're not going to go into the fringes and get into relativity. We won't do that, but you get the point, right? You guys. That's fine. No, I love it. I love it. Okay, so all of these, this is a table from your book. There's a more extensive table in the appendix, and you'll maybe need to refer to that. But all of these are units, joules per mole Kelvin. Joules per Kelvin is the unit of entropy, but these are per mole, because if you had 2 moles, you'd have twice as much entropy. Okay, so S prime, these are standard molar entropies. And these are all at 298. That's why they're not 0, because they're not at 0 Kelvin. Why don't we do all these things at 0 Kelvin?
Everything be 1.
Because nobody's gotten to 0 Kelvin yet. There's people trying, they've gotten really, really close. But it's really, really a hard process. And you can argue that it is impossible because if you look at the ideal gas law, you also predict that the volume of particles is 0 at 0 Kelvin. And is that possible? No. Yeah, all kinds of crazy things would happen. So at 25 degrees Celsius, the standard entropy of a substance is the energy that's dispersed into 1 mole of that substance. And remember, entropy depends on the number of places to put the energy. So several factors affect the molar entropy of a substance. It's affected by the state. Gases, liquids, solids have different amounts of entropy. It's affected by the molar mass, the particular allotrope, the molecular complexity, and the extent of dissolution if you've got something dissolved in a solvent. So we'll talk about these very briefly, one at a time. So the state of the matter, that always sounds funny. The state, the State of the Union. Well, was it a solid or a liquid? That's what the chemist in me thinks. The state of matter, gas, liquid, or solid, will affect the amount of entropy. The entropy of a gas is larger than a liquid, which is generally larger than a solid. So if we look at water in the liquid and gas state and we compare the molar entropies, we see that the molar entropy of the gas vapor, water vapor, is much higher than that of the liquid. Gases have more energetically equivalent places to put their energy. They have more types of motion, and they are more widely dispersed in space as well. The molar mass affects the amount of entropy. If we look here at this table, we're comparing entropies of noble gases. So these are all atoms. Their molar mass is increasing from, no, that's not the molar mass, that's the entropy. We know that the molar mass increases. If we want to know what those are, we could look at them up there. As the molar mass increases, the entropy of the particle increases. This is one that at this level we cannot really explain to you satisfactorily. And so this is the best your book came up with. The energy states associated with the motion of heavy atoms are more closely spaced than the energy states with lighter atoms, and so there's more dispersal of energy for a larger atom. It's not a real satisfactory explanation. Entropy increases with molar mass. This trend only holds if the substances are in the same state. You can't compare water in the gas state with carbon dioxide in the solid state, because the difference due to the state is really big. Allotropes. Remember what allotropes are? Those are different forms of the same element.
Oh, yeah.
Some elements have different allotropes. We are familiar with two of the allotropes of carbon: diamonds and graphite. You might have a diamond on your finger, and you probably have graphite in your pencil. You know that their properties are very different, but they are both pure carbon atoms. The entropies of these allotropes are different. The diamond has a much lower entropy, 2.4, about half of that of carbon in the graphite allotrope, because the arrangement of the atoms is different. In a diamond, we have a three-dimensional lattice, and the particles are fixed in that three-dimensional lattice. Carbon has two-dimensional sheets. That's why it's slippery, because there is sliding that occurs between these sheets of graphite, and so there's greater entropy there because there's more places to put the energy. Molecular complexity. So again, looking at just a single state of matter, here we're looking at gases. Entropy is generally going to increase with increasing molecular complexity. What does that mean? Well, let's look at argon and nitrogen monoxide. So argon is an atom, and nitrogen monoxide is a diatomic molecule. It's got two atoms bonded together. That is more complicated than just a single atom. That's what we mean by molecular complexity. Here, if we're looking at molar mass, which we know is also a factor, these molar masses are similar, but the entropy, the standard entropy, is different. So NO is more complicated. It has a larger entropy than argon does, because there are more places to put energy. Argon has translational motion. It can move back and forth, but so that's translational. These are both gases, so they can go through space, right? Nitrogen monoxide also has rotational motion. Why does argon not have rotational motion?
Single atom.
It's a single atom. And if we think of atoms as being like little hard spheres, you could say, well, yeah, but it could spin. Not really, because what is it that's spinning? The electrons? They're going all over the place anyway. An atom can't really spin around like a planet does. So argon has no rotational motion. And then we have this vibrational motion of the bond. The bond can stretch and squeeze and stretch and squeeze. That's another place to put energy. Argon can't do that. The more atoms you have in your molecule, the more possible places you have to stick the energy. If we look at carbon monoxide and ethene, their molar masses are virtually identical. Their standard molar entropies are not. Why? Well, here we've got 2 atoms, and then we've got 6 atoms. Greater molecular complexity. Down here we're looking at molar mass and molar complexity both increasing. So these are getting more complex, and the molar mass is getting larger, and so we see that those two trends add together and we get entropy increasing. So these are factors that you should keep in the back of your mind in case you need to compare 2 atoms or molecules, which one has higher entropy. And then there's dissolution. So if we dissolve a crystalline solid into a solution, that will generally increase the entropy. And this should make sense, because here you've got your little crystal of salt, right? You've got sodium chloride, sodium chloride, sodium chloride, and it's all nicely arranged, right? What happens when you dissolve it? They spread apart and they go throughout the solution. Dispersal of energy, positive entropy change. So if we look at potassium chlorate, which you guys probably feel like you've looked at potassium chloride a little too much. Or no, that was iodate, never mind. It's not potassium iodate, your friend. A solid versus aqueous, the aqueous has a higher entropy. So how do we calculate the standard entropy change for a reaction? Well, this is done much like we calculated standard enthalpy changes for reactions. When you write it in words, or even when you write the equation, it looks all complicated, and yet it actually isn't. So just don't tune out yet. So we subtract the standard entropies of the reactants multiplied by their stoichiometric coefficients from the standard entropies of the products multiplied by their stoichiometric coefficients. So if we look at it in an equation, what we're doing is we're taking the standard entropies of the products, subtracting the standard entropies of the reactants. Now, those are standard molar entropies. So if we have 2 moles of something, we're going to have twice as much entropy. And so that's where the coefficients come in. Those are from the balanced chemical equation. So N in here, NP represents the stoichiometric coefficients for the products, and NR would be for the reactants. And just note, standard enthalpies are always non-zero at 25 degrees Celsius because they're 0 at 0 Kelvin. 25 is not 0 Kelvin. They can only be 0 at one place, so they're never going to be 0. Let's do a calculation. Calculate the change in entropy for this reaction. I brought my book in because we need a table. It's Appendix 2. So what we need here is we need the standard entropies, standard molar entropies for these. So delta S, no, not delta. We need S0. So for H2S, I'm going to look it up in the table under sulfur. So the next page, H2S, make sure you get the state correct. So we want the gas, so that's 205.8. 205.8. And all of these are in joules per mole Kelvin. And then oxygen, O2 gas, the standard molar entropy is 205.2. And then we've got water in the gas state, 188.8. And then SO2 in the gas state, 248.2. Those you have to look up in a table or they'd have to be given to you. I would definitely not spend any time trying to memorize those. So what we're going to do is we're going to take the products minus the reactants. These units are joules per mole Kelvin, and it's for the molar quantities specified in the reaction, in the chemical equation. So 2 of these, 3 of those, 2 of those, 2 of those. So like a lot of things, it's products minus reactants. It's final minus initial. So delta S standard reaction is going to be 2 times 188.8. I'm going to leave the units out because it gets really messy. Plus 2 times 248.2. So those are the products minus, I didn't conserve space very well there, 2 times 205.8 plus 3 times 205.2. And what does that come out to? Okay, I'll do it with you. It's a race. minus 153.2. What units are on that? Joules per Kelvin. Because what we're doing here is 2 moles times joules per mole Kelvin, and so the moles all cancel out. Any questions? So the change in entropy is negative. Is that what we would predict by looking at the chemical equation? Number of moles of gas in products and reactants. Here we've got 5 moles of gas and 4 moles of gas. Fewer particles, lower entropy. The change in entropy was negative.
Yeah.
Any questions?